While it's useful to be able to quantify and describe the direction of magnetic fields that are generated, what we really ultimately care about is the forces that these magnetic fields will apply to specific objects. So this is going to be the first of two videos on those magnetic forces, this one specifically on moving charges. So let's consider this pair of objects. One is simply a charge of some sort moving with some velocity v, and the other is just a bar magnet. And we know that when this charge moves, it not only generates an electric field, it generates a magnetic field. And a magnetic field will apply a magnetic force to a magnet. However, that should also go in the reverse direction, because what would be the other half of this Newton's third law force pair? Well, it would be that the magnet should apply a magnetic force through its magnetic field to the moving charge. So let's see how exactly that would work. So we have right here a very large set of magnetic poles, and we know that there would be a magnetic field going from the North Pole to the South Pole. Now this could either be, these poles could be connected off the screen, or they could be the part of two different magnets. Doesn't really matter. We just know that the magnetic field is directed downward in this setup. Well, if that's the case, let me go ahead and introduce three different positive charges into this field. Now the first one over here on the left is going to be not moving. The one that's in the middle we're going to say is moving parallel to the field, so we'll say it's moving downward. And the one on the right we'll say is moving perpendicular to the field, so let's say it's moving to the left. Well, how exactly will the magnetic field apply forces to these individual charges? Well, let's look at the first one. Well, the one that's not moving is actually going to experience no magnetic force. And this makes sense because, remember, it's moving charges that generate magnetic fields, so only moving charges experience magnetic forces. Well, let's look at the second one, the one that is going parallel to the magnetic field. And interestingly enough, it actually doesn't experience a magnetic force either. So if it was moving up or down parallel to these field lines, no force at all. And lastly, let's look at the one that's moving perpendicular. Well, when it moves perpendicular, it actually does experience a magnetic force, and that magnetic force is going to go out of the page or out of the screen. Now that's hard to visualize here. I tried to draw it as 3D as possible, but that vector should be coming basically straight at you in a third dimension. So what conclusions can we draw from this? Well, an electric charge experiences a magnetic force if it is moving perpendicular to the magnetic field. So a couple of key details here is, one, if it is not moving, it will experience no force. And two, if it's moving parallel to the magnetic field lines, there will also be no force experienced. Well, additionally, though, what about the direction of that force? Well, that force is actually going to be in a third dimension compared to the motion of the charge and the direction of the magnetic field. So right here, I have, for instance, let's look at these three axes. This is just like Cartesian coordinates. I have x, y, and z. These are all basically perpendicular to each other, representing the three different dimensions. Y would be to the right and left, z would be up and down, x would be into the page or out of the page, though I know it's kind of hard to visualize that here. So if we look at this particular charge, its velocity is to the right, the magnetic field is up, it would actually experience a magnetic force coming out of the page in this third dimension. So how do we calculate the size of this magnetic force? Well, we're going to use this equation here, that the magnetic force is equal to QV cross B. And let's go ahead and first talk about what all the variables mean. So Fm is the magnetic force in newtons. Q is the magnitude of the charge. So notice that magnitude is really, really important. We'll see that more in a minute, but that's in coulombs. V is the velocity in meters per second. And B is the magnetic field strength, or in other words, the magnetic field intensity in Teslas. But what exactly is this x here? Because you might be thinking, okay, it's just a multiplication symbol. But the thing is, though, is that, Q and V are multiplied here, so why do we have this fancy symbol? And additionally, if you noticed a second ago, I said cross, not multiply. So what exactly is going on there? Well, what that cross actually is a form of vector multiplication. Now, we learned in AP Physics 1 how to add vectors together, or subtract them, using the tip-to-tail method. And additionally, you learned how to multiply a vector by a scalar, so something with direction by something not with direction. All it did was either basically enlarge the vector or shrink it, depending on if that scalar was greater than 1 or a fraction of 1. Now, the thing is, though, is that we didn't really talk about specifically vector multiplication, even though you'll see in just a second, we did it. I just never told you that we were doing it. Now, there are two different forms of vector multiplication, known as a dot product and a cross product. I'm going to go ahead and warn you now, we're not going to go into all the details of how they work. That is really a conversation for your math class. Specifically, you learn about these usually when you get to vector calculus, or in other words, calculus 3. But we're going to learn how to apply them, even if we don't understand all the mechanics. So let's first look at a dot product. A dot product is written as vector A dot vector B is equal to AB cosine theta. Now notice, I put the arrows over vector A and vector B, but I didn't put arrows over AB on the right side, and that's because they are then scalars. It's just the magnitude of those vectors. So just the magnitude of A times the magnitude of B times cosine theta. And what this is telling me, that theta is the angle between vector A and vector B, the specific, whatever it might be. And so what that results in is that if A and B are parallel, well then the angle between them would be 0 degrees, and cosine of 0 is 1, so we would get some maximum value. The dot product would just be A times B. But if they are perpendicular to each other, or at 90 degrees, well, cosine of 90 degrees is 0, so if we have A and B perpendicular to each other, their dot product is actually 0. It's a minimum value. And the dot product is often known as a scalar product, and the reason why is because we start with two vectors, A and B, and we actually end up with a scalar, because the magnitude of A times the magnitude of B times cosine theta, there's no vectors there, it just becomes a scalar directionless value. Now, we actually saw this last year in the calculation of work, though I never said it in this way. So remember, work is a scalar. It's a change in energy. It doesn't have direction, but it's equal to F dot delta x, or the force dot the displacement, which are both vectors. We wrote it as F parallel. Usually we said distance instead of delta x, but it also works. F parallel delta x, or F d cosine theta, but now we have F delta x cosine theta. What about a cross product? Well, a cross product, we have A, vector A, cross vector B is equal to AB sine of theta. Notice once again those are scalars A and B, magnitudes of A and B, times, and I have a little here, you notice it's a C with a caret. And I'm going to talk about that in just a second. Let's first talk about the magnitude of this, which would be AB sine theta. Well, if the vectors A and B are perpendicular to each other, you're going to get a sine of 90 degrees, which would be equal to 1, and so the cross product, if they're at 90 degrees, will just be A times B, just their magnitudes combined. If instead those are parallel to each other, well, sine of 0 degrees is 0, so if they're parallel, the magnitude would just be 0, and that's a minimum value. So we get a maximum when they're perpendicular, minimum when they're parallel. And this is actually something known as a vector product. The reason it's known as a vector product is we start with two vectors, A and B, and we actually end with a third vector. Well, what exactly is this third vector? Well, it has the magnitude of AB sine theta, but it just has the direction of C. So all this is telling me is that this is basically direction only. It's only telling me the direction of the vector. It has no magnitude. So it's saying it's this magnitude in the C direction. And where if I look at this diagram here, you have A and B and the angle in between them. C is in a third dimension. So when we say C hat, what we're saying is the cross product is in the direction of C with that magnitude. And once again, we actually did this last year too, and the example would be with torque. So the calculation for torque, we were used to tau is equal to RF perpendicular. So when you had the lever arm and the force perpendicular to each other, you had maximum force, but when they were parallel, it's like basically pushing in a lever, it doesn't do anything, and so it would be 0. But the actual calculation for this would be R cross F, and you would actually have a third dimension here. We didn't bother with the direction of torque. We usually just said counterclockwise or clockwise just to keep things simple. But unfortunately now we really have to start dealing with this third dimension because the charged particles are going to be moving with a force in a third dimension. So when we see this equation, the magnetic force is equal to QV cross B, there's a couple of things we need to keep in mind. First, how do we determine the magnitude of this magnetic force? Well, we can just use QVB sine theta, where Q is the magnitude of the charge, V is its velocity, B is the magnetic field in Tesla, and theta is the angle between the motion of the charge, or V, and the magnetic field, or B. So whatever that angle is between them, that's what we put into that equation. Now, one thing I do want to quickly note is this actually shows us that a Tesla, which we abbreviate with capital T, or the measure of magnetic field, we can actually define as a Newton per Coulomb times meters per second, because if I was to divide these over, I would have a force over a charge times a velocity. So this is actually a definition of what a Tesla is. So to find the magnitude of that magnetic force, we just use QVB sine theta. But how do we determine the direction of the magnetic force on a moving charge? Well, let's look at, once again, this scenario here. I've got two poles, north and south. The magnetic field is going to the left because they go from north to south. And let's say this particular charge, positive charge, is moving upward through the field. And the question is, okay, well, what is the direction on this charge? Because it's moving perpendicular, so there will be a magnetic force. And what we actually do for this is something known as the right-hand rule. Now, we already learned one right-hand rule. This is a second version of it. So now what I want you to do is actually follow along with me, and I'm going to see if I can figure out what the direction of this magnetic force is. So use your right hand, hold it up, and let's go through the details. First, the direction of the charge's motion, its velocity, you're going to use your thumb for that. So let's point our thumb upward. Then the next piece we're going to do is say, all right, now that I've got my thumb upward, the magnetic field is defined by my fingers. So I'm going to move my hand, so I've got my thumb up, and I've got my fingers to the left. And the magnetic force is then defined as the direction that your palm is facing. So velocity up, magnetic field to the left. My palm is pointed toward, coming out of the screen from your perspective. So the magnetic force would be out of the screen. There is a second way we can do this that I've seen some people do. There's multiple versions of the right-hand rule, where I've seen people instead do it like this, where they basically hold their thumb, their pointer finger, and their middle finger at right angles to each other. It kind of looks like you're doing some sort of strange hand signal there. And we put, once again, our thumb in the direction of the movement of the charge, our pointer finger in the direction of the magnetic field, and our middle finger will be in the direction of the magnetic force. So once again, coming out of the screen or toward you. Now, a really important point to note here is that this is only the case for positive charges. If we flip the charge to being a negative charge, it's actually going to go in the opposite direction. And you have a couple of different options for doing this. Either one, you can use the right-hand rule and whatever you find, just flip it, go the other way, the opposite direction. Or when you're using negative charges, you can use your left hand. I don't care. I know when I was younger, I prefer doing right hand, left hand, but I also know that if you have issues distinguishing between your right and your left, you probably just want to stick with one and figure that you would just be reversing it. Alright, so let's go through an example. Let's say we have this +2 millicoulomb charge moving to the left at a velocity of 350 meters per second. Keep in mind, high speeds are very common here because these are very, very tiny charges. They can move very, very fast. And they're going through a magnetic field that's directed at 0.8 Teslas downward. And the question is, at this exact moment in time, so when it's moving exactly left and the field is moving exactly down, what is the magnetic force at the charge at this point in time? Alright, so we're going to need to find the magnitude, and we're going to need to find the direction. So let's first do the magnitude. Well, to find the magnitude, we're just going to use Fm is equal to QVB sine theta, where Q is going to be the charge, so that's going to be 2 times 10 to the minus 3 coulombs, V is 350 millimeters per second, and B is 0.8 Teslas, and since they are perpendicular, the charge and the magnetic field are perpendicular to each other at 90 degrees, we get sine of 90. We multiply those together, we get 0.56 newtons. So that's the magnitude of the magnetic force. What about the direction? Okay, we got to use our right-hand rule. So we're going to take our thumb and stick it in the direction that the charge is moving. So that's going to be going to the left. We're going to take our fingers and we're going to direct them downward because that's the direction the magnetic field is going. And once again, we are going to get a magnetic force going in the direction of my palm, or from your perspective, out of the screen. So, the magnetic force would then be 0.56 newtons out of the screen. All right, let's do another one, and this time I want you to try doing it on your own, and let's see how you handle it. We have got a negative charge, that's negative 5 microcoulombs, so that's times 10 to the minus 6. We have a magnetic field of 1.5 teslas going into the screen, or into the page. Remember, the X's show you the backside of the magnetic field lines. If it was dots, that would be the front side. So this is going into the screen. And the velocity is 600 meters per second. So go ahead and figure out what the magnitude and the direction of these need to be. Hopefully you gave it a shot. So let's first off figure out the magnitude. We're just going to use QVB sine theta. And this one is easy. So the Q is 5 times 10 to the minus 6 coulombs. Remember, it is the magnitude of the charge, so we don't need to have the negative sign. We just use 5 times 10 to the minus 6. We put in the velocity, we put in the magnetic field. Once again, it's directed at 90 degrees because the charge is moving up. The field is into the screen, so those are 90 degrees relative to each other. And we get a magnetic force of 0.0045 newtons. But what is the direction? All right, so take my right hand. I'm going to have my thumb point in the direction that the charge is moving. I'm going to go from your perspective. So the magnetic field lines are going into the screen. So I've got charge going up, magnetic field lines going into the screen. So the charge should be moving, it appears to be, to the left. It should be a leftward force. But this is a negative charge, not a positive charge. If it was a positive charge, it'd be moving in the direction of my palm or to the left. Because it's negative, I need to flip it. So it's in fact going to be moving to the right. Now let's show you the other way to do that. If I used my left hand, I would say that the charge is moving up. The magnetic field lines are into the screen. I'm doing this from your perspective. And therefore the force is in the direction of my palm, which is to the right. So we get the same answer either way. Do not be weirded out by the fact you're going to be like moving your body around to figure out the direction of these. That's totally normal. Now, one last point to bring up is let's kind of look at the scenario we just looked at. We had a magnetic field going into the screen. The charge was moving upward, and it's a negative charge, so the magnetic force was directed to the right at this moment in time. Well, as the charge continues to move up and experiences that force to the right, its momentum is going to continue to pull it upward, but that force is going to be basically pushing it in the rightward direction until eventually it's moving to the right. Well, what would be the direction of the magnetic force now? So I'm going to use my right-hand rule again. Let's say that the charge is moving to the right. I'm doing this from your perspective. So to the right, the magnetic field lines are into the page. So the force would be going up, but it's a negative charge. So in fact, the force is actually going to be directed downward. And then once again, its momentum carries it more to the right, but the force pushes it downward until eventually it's moving down and the force goes back to the middle. And once again, we get this again. And what we're going to notice is that this particle, if the magnetic field is big enough, it is actually going to be taking a circular path inside of this magnetic field. In fact, charged particles always move in circular trajectories through magnetic fields. Even if they don't go through a full circle, they'll go through a circular arc until they eventually escape the magnetic field. Well, additionally, if we look, this magnetic force is always towards the center, so it is center-seeking, so the magnetic force is actually an example of a centripetal force. Now, I know it's been a long time since we've discussed centripetal forces, but remember, that means that the force is perpendicular to the charge's velocity or its motion, and that this basically changes the direction of the particle, but it does not speed it up. In fact, these magnetic forces will cause the charges to move in different directions, but it's not going to cause them to speed up or slow down. And one last thing is that if we know that Fm is equal to the centripetal force, well, what was that equation? Well, this would be QVB. We're going to assume they're perpendicular, so I'm just going to get rid of the sine theta, assume it's full magnitude, and the centripetal force is mv squared over r. And we can use this relationship to solve problems on occasion. For instance, let's say a proton is moving at a constant speed of 20,000 meters per second as it takes a circular path through a 0.2 Tesla magnetic field that is perpendicular to its motion. Don't really care how it's perpendicular, but we were told it's perpendicular. And we want to determine the radius of this proton's circular trajectory as it goes through this magnetic field. Well, how exactly can we go about doing this? Well, let's equate the magnetic force on this charge to, well, it's a centripetal force. Remember, centripetal force is not a type of force, it's just a way to describe forces. So the magnetic force is QVB, the centripetal force is mv squared over r, and we're looking for the radius of its path. Well, a couple things. First, I notice I can cancel one of these v's, And then if I rearrange it, I get that R is equal to mv over qb. So let's go ahead and stick in our numbers. You're going to have to go look up the mass of a proton, and that was 1.67 times 10 to the negative 27 kilograms, times 2 times 10 to the 4th meters per second, over the charge of a proton, which is 1.6 times 10 to the negative 19 coulombs. Remember, that's the magnitude of the charge. And the magnetic field is 0.2 Tesla. Multiply and divide those all out, and we get a radius of 0.001 meters, or 1 millimeter. That would be the radius of its little circular path. So what are the takeaways on this first video of magnetic forces, specifically discussing magnetic forces on moving charges? Well, one, can we determine when magnetic fields apply magnetic forces to electric charges? Charge has to be moving perpendicularly, or at least partially perpendicularly, to the magnetic field. Two, can we determine the magnitude and direction of the magnetic force on a moving charge? The magnitude being equal to QVB sine theta, and the direction using our right-hand rule. And lastly, can we analyze the circular motion of an electric charge in a magnetic field as an example of centripetal motion?